So, Joe Carroll will be presenting the Electrodynamic Debris Eliminator, opens LEO for aluminum recovery and reuse, and perhaps this aluminum can be used for Professor Shakarova's landing pad.
Yes, take it over, Joe. And more than that, the rocket itself. So you have the presentation ready. This is work that I've been interested in, but skeptical of electrodynamic tethers for 25 years since I first met Jim McCoy. Okay, and what really made me a believer is a phone call from Eugene Levin, my coworker. Stand up for a second, Eugene. And if you've got questions, you can. I'll be here the rest of the day. Eugene, you also. You can ask either of us and pick our brains because there's real need here. It sounds too good to be true, but there's real need here. Eugene called me about 8 years ago. We were working on an electrodynamic tether. We had worked on a mirror reboost tether, and stability problems are a big issue, trying to keep the vertical tether stabilized when you're dragging something heavy at one end and there's nothing on the other end except mass decay to bring along. And we were working on this project that Jerome Pearson was able to get funded from the Air Force, Kirtland. And Eugene said, Joe, I think we ought to spin this sucker. And the typical model of an electrodynamic tether is something in equatorial orbit. The field lines are like this, and it's at right angles, and it's very easy to imagine. You get the same eastward thrust all the way around the orbit. The problem is that nobody likes equatorial orbit for LEO. They love it for GEO, but nobody likes it for LEO. About 90% of the orbital debris is in inclinations beyond 70 degrees, far closer to polar than equatorial. And we start looking at the angles of the field and the tether, a hanging tether it's really hopeless near polar. Okay. Well, Eugene's idea that we should spin it, it stiffens it, but more importantly, it allows you to have attitudes that you can't have otherwise. So just credit to Eugene for realizing that we need to spin it. And a bit later, I'll go through some calculations, but I'll do it when the right slide is visible. Okay. Right now, we have some funding for the next month. We're doing work, actually 2 weeks, and then we have 2 weeks to get reported. It's a DARPA Phase 1 SBIR. And we've got our Phase 2 proposal, and we'll see whether this is going to go ahead. Let's look at debris. Okay. Everybody hears about the little pieces of stuff that the space station maneuvered to avoid. You know, I call them hubcaps and fragments of spacecraft. And one reason to call them hubcaps is that there are about 4 of them for each car, for each large spacecraft. And the largest spacecraft are typically, you know, like a ton to several tons, up to 8 tons. For each of those, there's about 4 small pieces that are large enough to track, but less than 2 kilos. Okay. When you look at it from an object count, the space station has to mostly dodge hubcaps. But when you look at it from a debris generation problem, it's really cars running into each other because they have most of the area, most of the mass. And as we found with the Iridium Cosmos wake-up call, I won't call it a collision, I'll call it a wake-up call. The possibility of cars running into each other and making not just hubcaps, but bullets, which are objects heavy enough to be lethal at hypervelocity, but too small to track. Okay? The real problem is not the hubcaps that the ISS dodges, but the 50 bullets that it doesn't dodge for each hubcap that it does dodge. Okay? That's the real debris problem. And to deal with the bullets, you have to get rid of the cars, not the hubcaps. Okay? Now, when you start looking at this in detail, you find things like there's over 2,000 tons of debris in low Earth orbit. Now, you'll see different numbers for debris because they usually lump LEO and GEO. And the problem in GEO we can't tackle very readily with EDI. And even if we could, its productivity is so much greater in low Earth orbit, we should clean up LEO completely before we even scratch our heads to think about GEO. But the LEO debris is 2,100 tons, which 2,100 metric tons is almost exactly the launch weight of a shuttle would have, including all the propellants. Okay, this is a large amount of mass. Okay? If, by the way, shuttle external tanks had been put in orbit, that mass would be 3.5 times higher. So most mass in low Earth orbit is not necessarily satellites or former satellites. Over half of it's spent stages. Okay? The real interesting complication in this that makes it not a technical problem, but a diplomatic and political and economic problem, is that 72% of that mass is Russian. Okay? That is the interesting complication. That makes an engineer like me realize that this problem is going to be solved. The heroes in this are going to be the lawyers. Okay? So, tackle the other stages first. Okay? There are fewer types of masses, and they are unlikely to have weird advantages you didn't know about. And they're less likely to be militarily sensitive if it's going to be a U.S. entity collecting Russian debris that we end up buying, and the U.S. State Department would have to agree to that because the registration has to transfer from Russia to U.S. probably. It seems like upper stages are an interesting thing to tackle first. Okay, and my suspicion is, especially with Russian stages, they seem to be mostly aluminum tanks. The Delta U.S. second stage is stainless steel tanks, and those survive re-entry. The Russian stages aren't, so at least most of them are aluminum with magnesium. They're analog to the 5000 series alloys. They should burn nicely on re-entry, but if you want to collect them and reuse them, they're a resource. So there's really a fork in the road we're going to come to, which is, do we get rid of it or do we collect it? Here's the story about mining aluminum in Leo. Okay, it's really highly clustered stuff in inclination and also in altitude. Okay, there are three clusters, major clusters. The Sun-Sync cluster is a very international cluster with roughly 1/4 each U.S., ESA, Japanese, and Chinese. Not much Russian. Okay, but the other two clusters are 97 to 99% Russian by mass. Okay. And you can really reduce the rate of debris generation if you collect this stuff. And you can make structures far larger than you could do with any lift vehicles. So let me just talk about potential processes and products. I'll get to, this is really the sales pitch part of it, and then the engineering part of how we're going to actually collect this stuff is later. If you just collect it, okay, just collecting it and sticking it on some analog of flypaper, that's all you have to do to make use of it as ballast for some ambitious tether that's going to catch and throw things, okay? So forget about paying launch costs. If all you have to do is collect the stuff, you can collect 1,000 tons in a total of 1,000 tons or so in 2 inclinations, and then use electrodynamic tethers to move into more useful inclinations. No fancy processing required. Okay, no manufacturing. The collection is the manufacturing. Then you can say, well, next step beyond that is cutting it up. Okay, and you can say, well, I'm not even going to really recover 100% of the ore. I'm going to recover 50 or 80%, whatever's easy. And you say, I'll just go after the bulk acreage of the skin. And if there's internal structure that's welded to the skin, I'll just cut between those. Okay? I'll just recover shingles. I'll make a standard size shingle. And by the way, there's one kind of Russian stage for which there are 292 copies, each weighing 1,400 kilos. That's 20% of the entire mass of everything in there, not just the stages. Okay? There's another type of Russian stage of which there are only 22, but they're another 8% of the mass. They weigh 8.3 tons each. Okay? So if you say, well, I'm going to just collect the stuff that's easy, and in the process, I'll be cutting lots of holes so what's left is going to re-enter and burn up far more readily, you're doing some very useful stuff, even though it's very limited. And what's the throughput that's required? Well, orbit mechanics require you to take about 5 years to collect this stuff. You have to wait for differential load regression. So you're collecting stuff at the rate of less than 1 a week. So it can take a week to process to cut the shingles. Okay, and that's okay. Then you can get really fancy, you go to metal bending and faceting. And by the way, you can, cutting up into shingles is enough to make shielding, micrometeoroid shielding and debris shielding. arbitrary shapes. And then the final step, if you're really ambitious, is melt processing. Feed the shingles into some processor, melt stuff, do vapor deposition. You can get better metal properties with vapor deposit under controlled conditions or molten spray than you can with ingot processing. There's a process called the Osprey process used by a British company that is used to make cylinder liners for Mercedes-Benz cars. Okay, you get better properties there than you can with conventional metalworking. You can get larger and heavier structures than heavy lift. I'll show you a silly example soon, but it's memorable, and you can improve on it. And then really, literally, and I mean this as literally as possible, the last thing you should do is use as a rocket fuel. All the other applications keep the material available. But if you find that in the future, reusable first stages and recyclable second stages make sense, a third to a half the mass flow to low Earth orbit may be aluminum alloys that are available for recycling. You don't even have to go collect them. They're going to your facility, your propellant depot or whatever. Well, if you have a surplus of aluminum, you might as well start using it as rocket fuel. Okay? Rather than, I'm not going to run most of you saw the video of the combustion, the magnesium combustion of dry ice yesterday, right? Yeah, okay. That would go here, okay? The first people to figure out how to do that really well, and I think it's going to be liquid aluminum, not solid powder, etc. I think there's some real niche there. So the pre-processing market, I'll go through this very quickly. The key thing is that it's going to be expensive to launch this aluminum, but this isn't like a conventional spacecraft where you get to choose what you launch. It's just something that's there. Let's say it's only worth 10% as much as retail launch costs. Well, Eddie can collect this stuff for a small fraction of that $1 billion. It's at least plenty of room for degree owners and buyers to figure out mutually beneficial terms. I think that even if you're only allowing an assumed price of the aluminum of 10% of current launch cost, there's still room to make money. Okay? Now, here's a very large structure. Most of you probably at one time or another visited the National Air and Space Museum. Okay? It's a large building. Okay? Imagine a spherical or cylindrical tank with the same volume as that with adequate safety factors allows a 3 psi environment. Okay? You can build that with the aluminum you can collect from just the spent stages low Earth orbit now. Okay? It's a silly thing to do, but it's memorable. Find 10 better things to do, okay? Now, here's how we get the stuff. Okay, electrodynamic tether. The basic concept is you've got the Earth's magnetic field, you've got a wire, okay? And you squirt electrons out at one end using either a hot wire emitter or hollow cathode for large currents. And let them close the ionosphere and then collect them here. They have either a source of power like a solar array, or you use EMF. And at certain orientations, as you're going through the field, you've got a large EMF. And if you want to go down, you can harvest that EMF, let it run the system for you, then you operate the generator load. Or you can push the current the other way with external power and climb. Now, let me just go back. I don't want you to believe my claims. I want you to calculate them myself. Okay, calculate them yourselves. Take a 1 square millimeter wire, 1 kilometer long, of aluminum. It's going to have a resistance slightly above room temperature of about 30 ohms. Under the best conditions, going over the poles with its sideways, you're going to have about 300 volts per kilometer EMF at orbit velocity, 7,500 meters a second. Okay, that's going to give you 300 volts, 30 ohms, 10 amps. If you've got some way to get the electrons in one end and out at the other, or if it's a many kilometer tether, and so you've got enough area at one end and the mass of the hollow cathode at the other end is not dominant. Well, what's the orbit change rate of that going to be? Well, first of all, you're not always at the ideal attitude. When you integrate over a full turn, the thrust goes down by a factor of 2, the average. Integrate over a full orbit, it goes down by a factor of 2 again. However, that average course, if you run the numbers, 10 amps under the best case, ends up being 0.1 Newton average thrust for a wire section that weighs only 2.7 kilos. When you run the numbers in low Earth orbit, the decay rate is 400 kilometers per orbit. Okay. Stuff can be orbited, and by the way, remember I talked about this stuff being mostly aluminum? If you could get a stage to unwrap itself and then hit it with a laser to start an arc at one end, you can get stuff to deorbit itself in one day, in a few orbits. Okay. It's not aluminum wire, it's aluminum foil. It's reinforced with with quartz fiber and cyanate ester that bare aluminum runs real hot in the sun, covering about 15% of the area is enough to keep it from overheating too badly. The resistance is a little bit higher, it's about 35 ohms per kilometer. It's a little bit more than 1 square millimeter cross section. But this is the basic ingredient, okay? Now this is roughly a 100 kilo vehicle, but really what it is a collection of nanosats along 10 kilometers of this stuff, okay? And this is held together with a weak pressure sensitive adhesive. There are actually 2 layers of foil that are welded together, and both ends are on the outside. And so the deployment, we call it orange spinning deployment. You deploy by spinning the thing up, and every time you get it spin up fast enough, the tension is high enough that it unwinds. They take a week to deploy, but once you deploy, you can move all over LEO. Okay? You can climb 200 kilometers a day with the baseline amount of solar power. Based just on the resistance of the wire, you can descend up to 1,000 kilometers a day. Okay? You can change inclination or node by 2 degrees per day. And you can do this indefinitely. Here's the real challenge with Eddie, is that it's like a taxi that doesn't need a gas tank, okay? But it's limited to the city. It can't drive across country. Well, that's where taxi, something that you don't buy, you rent. That's the operating mode for this thing. It wants to be in LEO. It can do all sorts of repeated business. It does not make sense in the remotest to do one maneuver and then die. It makes sense to keep doing stuff. And so that's how why we added a rendezvous capability. Okay, this is a video of a bead chain net rotating, and it's basically a spinning macrame basket. Okay, and we've improved on the net shape. I don't have the video of that. We don't have any video of that yet. But this just shows that you can take something, hang it outwards from the end of a spinning object. It's spinning very slowly, like 10 revs per orbit or 0.1 RPM, and spin it about, the real thing would be spinning about 3 RPM. And you can have something out there that's the size of this room, okay? It weighs about 50 grams and is capable of, if you can move it around the stage and then pull it up, you can capture that stage. Now, the stage is rapidly tumbling, it'll climb out of the net, but one of the interesting things about spent stages that are made of aluminum is they de-spin themselves in the Earth's magnetic field. Okay, the time scale is months. Christophe Bonal of Arianespace was really excited to learn that when they're just starting to tackle the question of what to do about Ariane spent stages. 1 minute, okay. Let me go on real quick. But you don't really, with most objects, have to worry about the spinning, okay? Now, collecting stuff, again, orbit mechanics limits the rate. You have to wait until the object resets through your orbit, but you can do it in years, not tens of years. And then there's a sweeper scenario. There's one option where you collect stuff starting at sunset and gradually drag it down to ISS. And by the time you get to ISS, maybe half of ISS is ready to be recycled and join the heat. Okay. Another option that may be more attractive to entrepreneurs is that collect first scenario. You just collect the stuff, and the question of what you do with it is something that you make your decision later as to whether you can recycle them or just cut them to pieces or deorbit them. Variety of operational issues I hinted at earlier. Technology maturation, a lot has already happened, and we're going to be flying TEPSI, the Naval Research Lab, is the next experiment. It's just a triple CubeSat, but it's going to be really, really important. The advantage, we've got a large advantage over competing concepts. Okay? Let's see. Let me end with this. problem, and then we can show how we can subtract from it. What I'd like to do is hand out a one-page kind of cheat sheet on orbital debris in low Earth orbit. It should get you thinking about the question of whether is orbital debris really the first extraterrestrial materials that we should be processing.
Yes.
My take on it is, if we know